Did you take the SAT? Yeah. Okay, give me those scores and I'll put them on there. Okay. Yeah, just make it. Give me a copy and stop up with that. I'll put them on there.
All right. Do we have a calculator? Anybody need one? There should be some around on the desks. All right. So we've been talking about the last few days how we can find the area under a curve, and we were using the Riemann sum rectangles and trapezoids to help us do that. Today we're officially going to take a look at how we can use calculus to help us find the area under the curve instead of having to use all those ridiculous amount of rectangles to kind of approximate it. So the calculus behind this is referred to as the fundamental theorem of calculus. Fundamental meaning something pretty important. Okay, one big theorem that we're going to talk about this year. But before we actually get to that, I want to first see if we can figure out the area under this particular equation by hand. So notice how the notation, we have the integral, meaning area under a curve, from -2 to 1. So graphically, we can kind of fill in the little section that we want to figure out. Maybe we'll even highlight it while we're at it. Right, okay, so maybe we don't have to necessarily use a bunch of trapezoids or a bunch of rectangles to help us with this. Notice how this particular shape is a trapezoid, so we should probably be able to go straight there, like what the area should be. Do we remember our formula for a trapezoid, our area? 1/2 height b1 plus b2. Okay, so our height is x-axis, so it's 3 units. And then our bases, looks like we have 7 and 1. So our area should be 12. Okay, so let's see if we can get the same result. This one's nice because the area we're specifically looking for is a geometric shape, but we've seen previously when we did rectangles and trapezoids that that's not always going to be the case. So at least with this one, we can check our answer because we know what the area should be. All right, so the fundamental theorem, we're going to get down to it. What has been some of the criteria or conditions that we've seen from other theorems this year? Yeah? All right, same thing here. If f of x is continuous and differentiable on an interval, right, same criteria. If f of x is continuous and differentiable on an interval, then the area under the f of x graph from A to B is equal to, I'm going to use g of B minus g of A. And this g function is the antiderivative. Okay, the antiderivative of f of x. Remember we did a lot of that last week, like at the boards. You're working backwards, okay, aka an antiderivative. All right, so the calculus behind this, okay, if we want to solve the area by hand, we're going to have to first work backwards from the function that we're using. And then we're going to use these bounds to help us evaluate that function. Notice how it's the top bound minus the bottom bound. Okay, but you have to work backwards first. You have to find that antiderivative. So let's see if we can do that. Can we work backwards from -2x? what did we have previously? What can you take the derivative of that would give you negative 2x? Negative x squared. Okay, you have to use that reverse power rule. And then we have to work backwards from 3. You basically have to work backwards from everything until you get to that dx on the end. Which, by the way, we're going to go over today, like why that's actually there. If you work backwards from 3, what did you have previously? 3x, all right, and we always need a plus c. Okay, so there's our antiderivative. In terms of notation, we're actually going to put a little bracket at the end of that, and we're going to write the bounds again. This little bracket just means we're going to evaluate this expression from 1 and negative 2. Okay, so after you get done with your antiderivative, more often than not, you'll see that bracket at the end of it. All right, so here's our antiderivative. We figured out what this g of x represents, and now we're going to plug in our top bound and then subtract what we get when we plug in the bottom bound. So if we were to plug in 1 into all those x's, we get negative 1 plus 3 plus c. Okay, this is what we get if we plug in the top bound. Now we're going to subtract what we get when we plug in the bottom bound. So negative 2 squared is 4, but we have a negative out front, so that would be negative 4. Plug in negative 2 again, and we'll get negative 6, and then plus c. So if we simplify kind of what's inside the parentheses, negative 1 plus 3 is 2, and we have a plus c. Negative 4 minus 6 is negative 10, but you're subtracting that, so it's going to change to a positive 10. And then you're left with this plus c on the end, but you're really subtracting it, so minus c. What are we going to be left with? 12. What happened to the c's? They cancel. Okay, that's actually always going to happen when you have the bounds. This is what's called a definite integral. Definite meaning you can figure out a number in the end, that area value. So kind of moral of the story here, I know we've been writing the plus c, and that's definitely needed if you don't know the bounds. But now that we do know the bounds and we're going to be plugging those in, notice how the c is always going to go away. So if you don't want to write the plus c, that's completely okay. But that's only if you know the bounds. Okay, if you don't know the bounds, then you need the plus c. All right, so maybe we'll make note of that. Don't need plus c if you know the bounds. All right, and notice how by hand using some calculus we figured out the same area was 12. Okay, so what's nice is I know that this is easy because we were able to use a trapezoid, but now what if it wasn't a trapezoid? What if it was a crazy shape? We can still use calculus to help us get us there. All right, let's try the next one. So same line, we're going to do 2 to 5 this time. So here's 2, here's 5. Area under the curve to the x-axis, so we'll kind of shade in that region. Can we perhaps make an educated guess as to what this area should be? And then we'll actually prove it by hand. Say it again.
12.
12, why?
Because it's the same as the top.
Same thing? Okay, so it's the same size as that trapezoid, so it should probably have the same area. Let's see if we can get that same result. So by hand, we're going to work backwards first. We're going to have the same antiderivative as before. We don't need the plus c though, because we know the bounds. We'll throw in the bracket and write 5 and 2. Which bound do we plug in first? Do we plug in the 5 or plug in the 2? Can we think about what the fundamental theorem tells us at the top? Can we tell?
Two, Mrs. Brown.
Why?
Because the A and the fundamental theorem thing, wait, no, it's 5.
Why is it 5?
Because the you subtract G of B minus G of A.
Okay.
And B's at the top and 5's at the top.
B is the top bound. Okay, so plug in the top bound minus what you get when you plug in the bottom bound. Okay, this is after you work backwards. Okay, you have to work backwards first. So if we plug in 5, we'll get negative 25 plus 5, and then we got to subtract what we get when we plug in 2. So negative 4 plus 6. So this would be negative 10 minus 2. So we get negative 12. So Cole, you were close. Why is this one negative though? It's under it. Okay, all of the area is underneath the x-axis. Okay, so the area value is still the same, but notice how the sign, like we've seen in the past, is kind of telling you a location, okay, or a direction, if you will. So it's underneath the x-axis. Looks good. All right, let's go ahead and try the next one. Same function, different bounds. Negative 1 to 4. All right, so if we shade in the area, we'll have kind of our first triangle on the left and then the second triangle on the right. Can we perhaps take an educated guess about what our area should be here?
Probably 12.
Probably 12? Okay. I mean, the other ones are 12, so yeah. Let's check it out. Okay, so why 0?
Because they cancel each other out.
Oh yeah, we went over this one.
Why do they cancel each other out?
So one's positive, one's negative.
Okay, the same amount of positive has the same amount of negative, so probably going to cancel. Let's see if that happens. We're going to work backwards. Okay, antiderivative. Throw in the bracket, top bound 4, bottom bound negative 1. Don't worry about the plus C because we know the bounds. If we plug in the top bound first, we'll have negative 16 plus 12. And then subtract what we get when we plug in the bottom bound. So plug in negative 1, we'll get negative 1 minus 3. So negative 4 minus another negative 4 changes to a plus 4. Looks like we get 0. So this is what's kind of might be confusing. You're getting an area value of 0, but that doesn't mean you don't have any area. Okay, sometimes that might be the case, but it also could mean that you have the same amount of positive and negative area. We have to be careful with that. So you can kind of have two different conclusions there. Let's try the next one. Negative 1 to 3. Can we take an educated guess as to what this area might be? Maybe not numbered value, but should we anticipate a positive answer, negative answer, 0 answer?
Positive.
Why?
There's more up and down.
There's more area above than there is below. Okay, so let's see. Antiderivative, top bound 3, bottom bound negative 1. Plug in 3 first, so negative 9 plus 9. And then plug in negative 1. Negative 1 minus 3. So we get 0 minus negative 4 changes to a plus 4. We get 4. All right, so positive answer. More area above than below. Looks good. All right, our last one, 0 to 5. What should we anticipate? Negative. Okay, so antiderivative, throw in the bracket, top bound first. Negative 25 plus 5 minus the bottom bound when we plug it in. I think we just get 0. So it looks like we get negative 10. All right, negative like we thought. All right, so based off of these examples, we kind of have 3 different conclusions or 3 different values that we can get in the end for this area, and we're going to kind of summarize those on the next page. So at the top, it says, based on the results, what inferences or conclusions can you make about the value of a definite integral? Definite meaning you know the bounds. Okay, you're able to plug something in to get a number. So we kind of have 3 different cases. Okay, what if the area under the curve is positive? What if the area under the curve is negative? And what if the area under the curve is 0? Can we think about what's that telling us? And we've kind of already touched a little bit of this as we were going through the examples. Okay, if we look at the positive answers, that was the first one we did. We got 12. And then the last 3 on the back, we had 4. So what was special about the graphs of those? If you get a positive area answer, what's that telling you?
More above.
More above than below. Okay, so in the first example, all of the area was above, so that's definitely positive. But on the second example on the back, notice how more of the area was above than below. So just because it's positive doesn't mean all of the area is above. It just means most of the area is above. Okay, so most area is above the x-axis. Can we maybe write a statement that for the negative result? Yep, most area is below the x-axis. And what if it's 0? Same. Okay, same area above and below the x-axis. All right, I think those make sense based off the examples that we've seen. All right, now before we get to some more examples by hand, I want to go over why we have the notation that we do. Okay, so I'm just gonna, you don't have to write this down, just maybe let it sink in, pay attention. So why do we have the notation this? Okay, to represent the area under a curve. Are we familiar with this symbol? Have we seen that before?
No.
No, not at all.
No.
Okay, that's fine. It's not a common symbol used in high school math. That's why I don't think we've ever seen it before. This letter E means summation. So if I were to do like x equals 1, 3, and I do x, for instance, I would need to start with 1 and then plug in every integer between 1 and 3 into this value or into this function and add them all together. Maybe I'll change this to 5. So I plugged in 1, this is what I get. If I plug in 2, that's what I get. If I plug in 3, that's what I get. Plug in 4, that's what I get. Plug in 5, that's what I get. And you add all those together. Okay, so this just means add or summation. This is kind of the backbone of why we have this notation. So before we get to this, though, I want us to think about what f of x dx is representing. What does f of x also represent in terms of a function or a graph? Y value. Okay, so f of x equals y value. what do you think the dx represents? Have we seen that before? Yeah?
Like a small change in the x value?
Okay, we've seen dx by using this derivative notation, right? And derivative means slope. So you can also think about this as y2 minus y1 over x2 minus x1. So the dx is representing some change, small or big, between x values. Okay, so dx is a change in x value. So if you think about the Riemann sums that we were doing and think about the geometric shape of a rectangle, what happens if you take a y value times an x value? Okay, a change in an x. A y value means height. X value means, yeah, you get an area, right? This is a y value of height times a change in x, meaning a width. Height times width, or base times height, is the area formula for a rectangle. Okay, so the reason we have the dx on the end, why you absolutely have to write it, is it's representing the base of that rectangle that you draw for those Riemann sums. So this is telling us we're taking any height value we want times any change in x we want, small or big. Now in terms of our Riemann sums, how big do we want the changes to be for the base of a rectangle? How can we get very accurate? Tiny ones, right? So tiny changes mean more rectangles, which means more accuracy. Okay, so we're taking essentially a base, which was the dx, times the height, which was an f of x, and what did we do with all the rectangle areas that we found using a Riemann sum? We add them together. Okay, now depending on where you want to start, like maybe we want to go from 1 to 5, okay, we have that summation symbol. Now instead of using this, we simply use that integral symbol. So notice the connection. The summation from 1 to 5 of all those individual rectangles that we want to add together. Do we see the connection between the two? I know it's a weird notation, but it's coming or stemming from those rectangles that we drew. And this is why the dx on the end is so vital, because if you forget it, you're basically forgetting to multiply by a base, which means you're forgetting to multiply or find an area. Okay, so don't forget the dx on the end when you write your notations. All right, let's try some of these other ones, and then we'll check our result on the calculator. Okay, your calculator can actually find these by itself, just like it does derivatives. So maybe we'll check our work. All right, so for this one, we want to find the area under the curve of 2x minus x squared, specifically from -1 to 2. Now, we're not necessarily going to graph it to get a picture, because now that we have the fundamental theorem of calculus, we can do this by hand, but we'll use the calculator to check our work. Okay, you have to find an antiderivative first. Okay, you have to work backwards. So, can we work backwards from 2x? What did we have previously? Can we do a reverse power rule? X squared, okay? And then let's work backwards from x squared. That'd be 1/3 x cubed. All right, you don't need the plus c because we know the bounds. So we'll throw in the bracket with those bounds. Which one do we plug in first? 2. All right, 2 squared, 4. 2 cubed is 8, and then we have to divide it by 3. Next, we'll subtract what we get when we plug in the bottom bound. So -1 squared is 1. And then if we cube -1, it's still -1 divided by -3. So change to a positive 1/3. All right, so 4 minus 8/3 minus 1 minus 1/3. Let's see, 4 minus 1 is 3. -8/3 minus 1/3 is negative 9/3, which is 3. So 3 minus 3, 0. What's that telling us?
Equal above and below.
Equal above and below. Okay, so let's check it out. On your calculator, we'll turn it on. Normally we go to the math button, and if you scroll down to number 8, that was our derivative shortcut on our calculator. Notice though how number 9 says int for integral. So I want you to select number 9. Hopefully you get the boxes that pop up, because that operating system is going to be a little bit easier to understand. So we're basically going to type it in the same way we see it on our paper. And you can use the arrow keys to bounce around from box to box. All right, and if you hit enter, now my calculator is being very specific, but notice how this is scientific notation. You'd have to move this decimal 14 places to the left, but if we only round to 4 decimal places, that's going to be 0 anyway. Okay, so your calculator can give you the value. We can also check it out graphically. Okay, can you do me a favor and hit the y equals, and we'll actually graph this. Let's change our window. We're only going from -1 to 2. So I don't know, maybe I'll go from -5 to 5 so I can see everything. And I'll do -6 to +6 for the y's. Okay, so here's my curve. On your calculator, if you hit second calc, which is where we normally go to for like maxes, mins, zeros, intercepts, all that jazz, notice how 7 is the integral. It has that curly S, so you can select 7. And it's going to ask you some questions. Your lower limit or your lower bound, in this case, is -1, so you can just type in -1. And then the upper limit is 2. Now the moment you hit enter, it's actually going to highlight, which I think is kind of cool. It's going to shade in the region. So even though it doesn't necessarily look like equal area, because we have different shapes here, okay, it's not something as nice as a rectangle or a trapezoid, but we do have equal area below and above. I think it's kind of cool how it shades it for you. Okay, so you can visually see that region. All right, now this is only for if you have a calculator active section. Okay, realize how we should be able to do some of these by hand. All right, let's try the one on the right. We want to find the area under the curve from -2 to 3. Can we work backwards? Or maybe we should be careful not to jump the gun. Okay, because remember this is a theorem after all. We should really check the conditions first before we can actually go through with it. So what did we say the conditions were for like any other theorem that we've had this year?
Continuous and differentiable.
Okay, continuous and differentiable on the interval. So our interval's from -2 to 3. Is there some number that would cause issue with this function between -2 and 3? Definitely, okay, because it's discontinuous at 0. So before you jump the gun and immediately go into antiderivative, top bound minus bottom bound, check to actually make sure. If you did it by hand, okay, if you didn't check it, you'd actually get an answer. If you type it in on your calculator, though, it checks the conditions for you, and it should say error or not possible. Okay, so be careful. We'll say not possible because f of x is discontinuous at x equals 0. Okay, just like any other theorem we've done this year, you have to make sure the conditions are met before you go ahead and actually apply the theorem. All right, so keeping that in mind, what about the third one? Is there some number that would cause an issue between 1 and 4? Probably not, okay, because 0 would be a bad number, but it's not in the interval, so we're good to go. All right, so we can work backwards from this and then do top bound minus bottom bound to get our area value. I don't think, though, we can work backwards from it the way it looks right now. So can we rewrite it so we could use maybe a reverse power rule? You have any ideas? Let's see, we're dividing by one term on the bottom. So let's maybe divide each piece, yeah, split it up, divide separately. So 2x divided by x squared would be 2 over x. And then we would have 3 over x squared. All right, so we divided it separately, but again, I don't think the way it looks right now fits our reverse power rule setup. We want x's to powers, no fractions, no roots, no parentheses. So maybe we'll rewrite the first fraction as x to the negative first, and the second fraction as x to the negative second. All right, let's see if we can work backwards from here. Can we work backwards from x to the negative first? Nice. Okay. So if you try to reverse power rule, the new power would be 0, but you can't do 2 divided by 0 because that's undefined. So we know this is going to be a special antiderivative. It's actually a natural log. All right, so 2 natural log of x. We should be able, though, to do reverse power rule on the next one. If we add 1 to the power, that'd be negative 1, and then divide 3 by the new power, which would be negative 3. Okay, we don't need the plus c, though, because we know the bounds. All right, which bound do we plug in first?
4.
4, the top bound. Okay, so this would be 2 natural log of 4 minus, let's see, if I plug in 4, this would change to 3/4. The 4 would have a negative power, so you can move it to the bottom. Now let's subtract what we get when we plug in 1. So 2 natural log of 1 minus 3. All right. Do we know what the natural log of 4 is? Probably not. What about the natural log of 1? That's 0. Okay, so this is technically 2 times 0, which goes away. And we're subtracting a negative 3, which would change to a plus 3. All right, so there's our area. Maybe we'll get it as a decimal. 2 natural log 4 minus 3/4 plus 3. 5.022. Chop at 5 or round to 6. Up to you. Shrunk? Oh. Okay, then it'd be 5. Now, if you want to double check it, all right, let's do math down to number 9. Lower bound 1, upper bound 4. I'll type in 2x plus 3 in parentheses and divide it by x squared. 5.022526. Okay, so looks like we did well by hand. You can always double check if you have a calculator. All right, let's end things maybe with a trig one. No fractions, no roots, no parentheses, so we shouldn't have to really worry about working or rewriting this one at all. Let's just go ahead and work backwards. What did we have previously from a 2x? X squared. Okay, what's the antiderivative of cosine? What can you take the derivative of that would give you cosine? Sine. Okay, so plus sine of x. Upper bound 0, bottom bound 0. Or upper bound pi, rather. I think we really should check the conditions, though, right? As with any theorem. But I don't think 2x or cosine is undefined anywhere, because one's a line and the other one's a wave. So we don't have to worry about any discontinuity there. Which bound do we plug in first? Pi. All right, so pi squared plus sine of pi, unit circle. Sine of pi is 0. Now we're going to subtract what we get when we plug in the bottom bound of 0. 0 squared is 0 plus sine of 0. That's 0 as well. Looks like we're left with pi squared. All right, if you want to double check it, we'll do math. Number 9, 0 to pi, 2x plus cosine of x, 9.8696. And if I compare that to pi squared, notice how it's the same thing. All right, so we're good to go. So at this stage, we will no longer have to draw those really tiny, inconvenient, tedious rectangles because we can solve for area by hand using some calculus. And it just involves finding an antiderivative, which we already know how to do. All right, so we're just expanding on this area under a curve. How are we doing so far? Pretty good? All right, we'll stop there for today. We'll check out some more tomorrow.